Okay. So, in the last class we discussed Hermitian matrices and their properties. A special class of Hermitian matrices play an important role in our subject, and that is called positive definite, sometimes positive semi definite also. Matrices. Given a matrix A, say n cross n, it is positive definite or semi definite if number 1 A is Hermitian. So, it must be a Hermitian matrix. Number 2, for any vector x where x is non-zero, this thing x h a x, and remember in one of the previous classes I showed that even if A is complex, A has complex entries, x has complex entries, this is a scalar which is real. Matrix into column vector is a column vector, this is row, row into column is a scalar, and this is a real number. This I have shown. Now, for any vector x, if this real number is greater than 0, then it is positive definite. Definite. And if it is greater than equal to 0, it is positive semi definite. All right. This is a special class of Hermitian matrices. Now, for positive definite matrices, for it is a Hermitian matrix. So, eigenvalues are real, but if it is positive definite, eigenvalues are just not real, they are positive. All how? Suppose A x is lambda x, and since x is an eigenvector, x is non-zero, like x is non-zero. So, if I multiply this side, left hand side and right hand side called pre-multiplication, that is here if I multiply x h times a x, x h a x, this will be lambda is a scalar. So, take it in the front and it is real x h x. All right. Now, we have seen if it is positive definite for any non-zero x, x h a x is greater than 0, and here x is an eigenvector which by definition of eigenvector is non-zero vector. Okay. So, for a non-zero vector x, x h a x which is real is positive. That means, lambda x h x is not only real, it is greater than 0 if it is positive definite, and x h x, we all know x h x will be what if x has, suppose x has x 1, x 2 dot 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 x n, then x h x will be, I mean you make it a row vector and then there is take a transpose of this, it becomes a row vector, then conjugate every element, that times x. So, x 1 star into x 1, x 2 star into x 2, like that. So, it will be, this we discussed earlier quite a few times. And in this case, it is, see, as such it is never negative, real, because we are taking mod of a number which may be complex, but mod makes it real, real square. So, it is either 0 or positive, it cannot be negative, and our positive all are added, there is no minus, there is no subtraction of two positive quantities, so that the reality thing is negative or 0. So, they are only positively contributing. Therefore, if it is to be 0, either it is 0 or positive. If it is to be 0, every contributor has to be 0, every term. So, if this is 0, that means x 1 itself 0, because mod x 1 square 0 means mod x 1 0, and mod x 1 is 0 means x 1 has to be 0. So, like that. So, if it is 0, all the elements of x, they have to be 0, and therefore, x must be 0 vector, but x is a non-zero vector, because it is an eigenvector. Therefore, all the terms here cannot be 0. So, this is some are positive and others are 0, or maybe all are positive. So, sum together is not 0. So, it is greater than 0. So, if it is greater than 0, this is greater than 0, this means lambda also greater than 0, because this is greater than 0. So, lambda also greater than 0. So, if it is a positive definite matrix, then eigenvalues are strictly positive. If it is a positive semi-definite matrix, then instead of the greater than 0, we would have had greater than equal to 0, and then lambda into a positive quantity greater than equal to 0. This is positive, non-zero. So, lambda will be then greater than equal to 0. So, in case of positive semi-definite matrices, lambda greater than 0, greater than equal to 0. If it is strictly positive definite, lambda is greater than 0. So, if A is positive definite, that means A is Hermitian. In that case, we have said determinant of A for a Hermitian matrix is a product of the eigenvalues, and if every eigenvalue is greater than 0, so this product is greater than 0. Therefore, determinant is non-zero, therefore, the matrix is invertible. But if A is positive semi-definite, then every eigenvalue is greater than equal to 0. So, they can be equal to 0 also. In that case, the product which is determinant is not strictly greater than 0, it is greater than or equal to 0. So, I cannot say with 100% guarantee that A will be invertible, because if any eigenvalue turns out to be 0, determinant is 0. So, in that case, A will not be invertible. So, for invertibility, A must be strictly positive definite. All right. Now, consider a correlation matrix. Suppose I have got a vector of random variables, okay, or maybe I change the notation. I got U, a random vector. These are the random variables, in general complex valued. So, form E, I am not putting the subscript here, you will understand. U, U, H. So, that will be a matrix and E will be operating on each. So, only the random variables present in that term will be in the subscript, otherwise others will drop off, that we know. And this is called the autocorrelation matrix. Suppose R U U. All right. So, this is Hermitian, we have already said. We have already analyzed this kind of matrices. They are conjugate symmetric, I comma j and j comma ith element are conjugate of each other, which makes it Hermitian. So, Hermitian we have already seen earlier. There is correlation and covariance matrices are Hermitian. After all, covariance matrix we have shown, but in the case of covariance matrices, we took the mean, maybe mu 1, okay, and you can call this u 1 prime, u 2 prime. So, that is again a vector, and then covariance matrix becomes the correlation matrix of u 1 prime, u 2 prime dot dot dot. Okay. So, the same logic applies there. There is you can apply the same logic, you will find R u u also Hermitian, I comma j and j comma ith element are conjugate of each other very easily. You apply the same flow of logic, you will get this, there is nothing here. Okay. So, Hermitian is done, but is it positive definite? If positive definite, we can happily say that this is invertible matrix, because often we might require to invert this matrix to solve some equations. Okay. Is it invertible? that is it positive definite? For positive definite, that is it positive definite also? Positive definite. Positive definiteness requires two conditions. It should be Hermitian first, and there is one more condition. So, Hermitian is done. So, take any non-zero x as x1, x2 dot 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 xn means at least one element or more than one element will be non-zero. So, non-zero x. Then positive definiteness requires x h or I am not using the subscript or EU, is same R, and x. This should be, this is real, even if R is complex, x is complex. We have seen earlier and have just a while ago told that this is real. And if it is positive definite, this should be greater than 0, not just real, greater than 0. And if it is positive semi-definite, this should be greater than or equal to 0. So, let us investigate this. X h or x, that is x h or is E U U H x. All right. Now, one thing we see here, this is a matrix. Okay. This is a matrix, column vector into row vector, this is a matrix, and this is a column vector, this is a row vector. Okay. But this is x is not random, elements of U are random. Okay. As an example, let me see how to explain to you people. Suppose, just as an example, U is U1, U2, X is X1, X2. As an example, suppose this, there is just two elements, small n equal to 2. In that case, U H, we consider this part first. I will bring this U H E of that into x will be what? U H, U and U H means you will make it row and conjugate and then multiply U, then it will be expected value of mod U1 square, U1 U2 and then U1 U1 star U2 star, then U1 U2 star, expected value U1 U2 star, and then here expected value U2 U1 star, and then expected value mod U2 square. This into x1 x2. So, this times x1, this times x2. Okay. You can see since x1 and x2 they are not random, you will get the same thing if you take E and then U H, then push the x from outside to inside the expectation, because if you carry out U H mod U1 square, not the E operators, mod U1 square, U1 U2 star, U2 U1 star, mod U2 square, and then x1 times that, x2 times that added, x1 times that, x2 times that added, then E comes in. But E of this into x1, x1 is not random. So, it will be nothing but E of only this part, because this is random, x1 goes out like here, this into x1. Similarly, x2 into this, x2 into this quantity, then E over the product will be same as E over this the random part only, x2 outside, as is happening here, E of this part into x2. Okay. So, since x is not random from outside, you can bring x here. Okay. So, you get one vector, this into this plus this into this one vector, this into this plus this into this one vector. All right. This vector is a random vector because this vector is not a random vector, because after we apply expected value, that into x 1, they are not random, this into x 2 not random, because after expectation it is just mean average. So, it is not random. So, this part is clear. Okay. By the same way, x h then from outside, I have now x h. So, if I have an x h before it, so it can be seen that x h also can be brought inside. Very simple. Okay. I need some space to write, there is a problem. So, this is a matrix times x, is a column vector. Entries are not random, all right. So, you can see one thing, if you call this just a minute, if you call this some vector, say maybe small v, u h at x 1 x 2 their expected value. So, it is not a E v. Okay. So, basically u h and then x 1 x 2. So, mod u 1 square into x 1 plus this into x 2 and likewise E outside. So, this vector is random vector again. Okay. So, now originally I have x h times this. So, if I bring that x h and this entire thing, which is E of v. Okay. V is I denote as v 1 v 2, two elements. Then it will be x 1 h means x 1 star, x 2 star and E v 1, E v 2. And we multiply this by x 1 star, this by x 2 star. You will see you will get the and then add x 1 star times this plus x 2 star times this and add, that is what this is. But suppose I push x h before v, because x h is not random v. Then again what happens? E of x 1 star. So, this vector comes inside and v 1 v 2 as before. So, x 1 star v 1 E on that, but x 1 star is not random. So, it will go out like x 1 star just E of v 1, E of v 1. Similarly, x 2 star into this E on that, but x 2 star is not random, it will go out like here x 2 star and E of v 2. So, you get the same thing, all right. So, that means this will be x h r x, I can write x h r x in general, which is x h E of u h into x. So, x h can be brought in inside, x can be brought here. So, E of x h v and u h, this is x h u, this is u and u h x. X has from here gone in here, x h has gone in here. This is what? Okay. X h u, u h x. Okay. So, if u h x, u is a column vector, u h is a row vector, okay, because you transpose and then conjugate. So, a row vector times x, x is a column vector. So, row into column it is a scalar. So, this quantity is a scalar. Okay. You can this is x, so you can call it anything, maybe you can call it y, y is a scalar. Okay. Then if y, if UH x is y is a scalar, if I take y star, y is a scalar, scalar is also can be viewed as a 1 by 1 matrix. So, it is like YH, because y is a 1 by 1 matrix, first you transpose, you get back y only, then star, so you get this. But YH means this side, if I apply H, it will be XH UHH, so U, all right, which is my UHX, sorry, which is XHU. UHX I started with, I called it Y. If I apply conjugation on Y, Y star, which is like Y Hermitian, okay, I get this quantity. So, this is nothing but E of mod Y square, Y star, this is Y star, this is Y, E of mod Y square. So, this is what I take to the next page. So, if this quantity is either greater than equal to or equal to 0, okay, that we will see. We are dealing with the special case of correlation matrices or covariance matrices. Okay. For them, first condition was satisfied that this matrix is Hermitian. Second is it positive definite? Okay. So, I took a non-zero vector x and I found out XHRX. XHRX can be written in this kind of form, or you write and then XH can be pushed inside, X can be pushed inside. Okay. So, UHX I call Y is a scalar, because row vector into column vector. So, this is Y star, so E of mod Y square. One thing you can see, Y is a random variable, because even if X is a deterministic vector, non-random vector, elements of U, they are random. Okay. So, UHX will be a scalar like U1 star x1 plus U2 star x2 plus U3 star x3 and dot dot dot. So, all U1, U2, U3 they are present means this entire thing is random and its conjugate also random. So, E mod Y square is random, because Y is random and the expected value. But remember, it is mod Y square. So, mod Y make it real and positive and then square. So, this number can never be negative. Okay, this number can never be negative, either 0 or positive. So, expected value can be, if it is always 0, then only expected value will be 0, but if it is sometimes 0 and in some experiments it is positive, mod Y and therefore mod Y square positive, then average will be positive. So, this entire quantity will be either positive or 0. So, in general positive semi-definite. It will be 0 if mod Y square and therefore mod Y turns out to be 0 in every experiment. So, when you average by applying E, you still get 0. That is a very special case. But if that does not happen, in some experiments or maybe in all experiments mod Y is positive, or at least in some experiments positive, and then you average mod Y square, you will get a positive quantity. So, in that case it is positive definite. So, this is either positive semi-definite or positive definite. So, with that I go to the next page. This is what I had earlier, XHRX is expected value of mod Y square, where Y is a scalar and that was UHX. Alright, it is a scalar. So, this quantity is obviously greater than or equal to 0, because as I told, mod of Y real, positive and square. So, this can never be negative. So, average value can never be negative. If it is 0, that means in all experiments mod Y should be 0 and this is the average is 0. Otherwise, in some experiments at least it will be non-zero. So, when you average value will be greater than 0. So, it is positive definite. Now, when will it be equal to 0? That condition, that equal to 0 here means equal to 0 means Y equal to 0 always, UHX always. but UHX is, U as a column vector, so UH is a row vector with conjugated elements, and this is your x1 dot 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 x2 equal to 0 always, sorry. As I told you, if this expected value has to be 0, then y must be 0 in all experiments. Then only mod y 0, and therefore, in all experiments, and therefore, mod y square when averaged expected you get 0. But this means UHX this is equal to 0, which means U1 star x1 is a scalar of your choice. So, x1 U1 star is a scalar, can be 2, 3, 4 anything, then x2 U2 star and dot dot xn xn un star is equal to 0. I can take complex conjugate of left hand side and right hand side. Right hand side is 0, so that remains 0, and this you can say x1 star, which is again a known constant, times u1 x2 star times u2 and dot 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 xn star times un equal to 0. Suppose all the coefficients x1 star, x2 star, xn star, they are non-zero, and still this is satisfied. In that case, I can keep one element, maybe u1 on one side, take the other ones on the right hand side. So, u1 will be a linear combination of other variables u2, u3, un, even if not all are non-zero, maybe 2 are non-zero. I take the non-zero one, the other one on the right hand side. So, it will be u1 is minus x2 star by x1 star into u2. Okay. So, one random variable at least will be a linear combination of the remaining ones or part of the remaining ones. But that does not happen in practice usually, because when I have got such set of random variables, there is no such linear relation between them, then at least one of them is a linear combination of the remaining ones. Like as I told you, if I keep u1 here and suppose all are non-zero, it will be like this is non-zero, so it can go in the bottom. So, as though u1 is a random variable, but it is basically having a linear relation with the rest. So, if I know the rest, I know u1. Okay. That is, u1 does not have independence, we say they are linearly dependent. That does not happen in practice most often. Random variables are random, there is no linear relation underneath. In the background, there is no linear relation between them. That just like somebody's speech. You just suppose say something and I see the waveform. I take a sample. Samples are random, because next time I see the same waveform, I mean same speech, I will see a different waveform. Samples will vary. So, at every time point, samples are dancing, fluctuating. There is no linear relation between those samples. No way. If that happens, that means this cannot be equal to 0. So, if this is not possible, there is no linear relation between the random variables, they are purely random. Okay, they are independent of each other. We say linearly independent of each other, because I am taking a linear combination equated to 0. In that case, this fellow at least is dependent on the others, maybe more fellows are dependent on the others, that is called linear dependence. So, there is no such linear dependence within these random variables, they are purely random, like the speech example I gave. In that case, you cannot have this equal to 0 with non-zero coefficients, because when I talk of positive definiteness, x must be non-zero. There is at least one coefficient non-zero, or all coefficients are non-zero. So, non-zero coefficients there and these equal to 0 cannot happen, because that will have been linear dependence. There is at least one random variable is linearly related to others. Okay. Even if suppose this is a vector, only I want x to be, I have to have x to be non-zero. So, suppose you say, so let only one fellow be non-zero, others are 0. Let x1 be non-zero, others are 0. That will mean x1 times u1 star, or rather x1 star u1 equal to 0, and x1 is non-zero. So, that means u1 is a 0 random variable, because if x1 star u1 is 0 and x1 is non-zero. So, x1 star also non-zero. So, non-zero into u1 equal to 0 means u1 must be 0. That is, u1 is such a random variable which will take 0 value always. Okay. So, when you take a product with some non-random scalar, result is 0 in all experiments. But in practice, we do not encounter this kind of random variables, which in every trial takes only prefixed 0 value. So, we assume that does not happen. There is no linear relation between these random variables, between any pair or more, maybe between 2, between 3, or between all n of them, and none of them is a 0 random variable. That is, none of them is such that it takes 0 value in all experiments, which is a very practical case. In such cases, this is not possible for a non-zero x. Okay? Which means, in such cases, we can assume the matrix to be ought to be positive definite, because it will be actually greater than 0, equal to 0 ruled out. All right. And in that case, R will be positive definite, and therefore, R is invertible. So, in our future lectures, correlation or covariance matrices like R, we will take them to be, assume them to be positive definite, and then we can write R inverse. That is, we will assume this inverse exists. Okay, this much for this lecture, and from here I will pick up in the next. Till then, goodbye.